what is the subject about, what are the few examples, what are the basic underlying assumptions. Okay, so this is the syllabus for your unit 1. So we'll talk about equations. Let me get a pointer. Okay, so we'll talk about what are the basic equations for compressible flow, and we'll talk about shock wave propagation. We'll also talk about something called stagnation properties. Okay, and then we'll discuss about one-dimensional steady state equations, and we'll look at some examples. We'll talk about stream tube and some nozzle and diffuser and the pressure coefficient. So this is part of your syllabus for the subject for unit 1. Okay, now this is a new subject. So this is basically an extension of or a specialized domain of fluid mechanics, right? So what is new or what is the extra part that subject covers? Okay, what is not covered in a graduate level course of fluid mechanics that we are trying to cover in this gas dynamics? Okay, so first is that we'll be dealing with high speed flows. Okay, so we'll hear the term like supersonic, hypersonic. So in this course, we'll try to understand what these terms means. Okay, how do we define different regimes of flow and what is actually high speed? Okay, so for example, let us say any object is moving at 100 meters per second. So is the speed high enough? So what will you say? It is high or low? Yes, anyone? You people are connected or not? You people are there?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So please keep speaking, otherwise I will think I've lost connection. So my question is that we have a flow or any object is moving at 100 meters per second. So is this a that speed is high or that speed is low? Anything? It is not an exam. I want you to discuss. So 100
Sir,
meters.
we will decide it on the basis of Mach number now.
Correct. So it is relative. So for example, if I am designing a car, I will say 100 meters per second is very high speed. But if I am suppose talking about a rocket, so I'll say that 100 meters per second is a low speed. So it depends on, it is a relative term, and we look at how we define. So we'll define something called Mach number, and based on that we'll fix or we'll give some criteria that this is the range and how we talk about, let us say, supersonic or hypersonic flows. Okay, then for this subject there is something interesting or in addition to fluid mechanics. So general fluid mechanics examples, we see that the temperature is not changing because of flow. Okay, so there will not be appreciable change in temperature or density because of flow in normal fluid mechanics examples. But in gas dynamics or in compressible flow, we also say that there's a large change for density as well as temperature. And this brings us to compressibility effects. So we look at how do we define compressible, what is compressible, and how it affects your flow. This is something that we are going to discuss. So let us take some examples. So has anyone been to any aero show or seen any plane from close like this? Or you have seen any pictures? So can you see in the tail region? You see some structures are visible. These are called shock diamonds. So has anyone seen this or any photo like this? People are mute or what? Yes or no? Either you have seen or not seen. There is no third option. Right? So I believe no one has seen this. Hey, don't worry, I will not cut your remarks if you have not seen. But I want to know whether you have seen this or not. That is the only question. You see something in the tail region, right? In the exhaust, we see some structures. So has anyone seen it or not?
No, sir.
Okay, that's what I'm asking. So if you basically you will not see for commercial airplane, passenger aircrafts, this is not visible. This requires a certain amount of velocity which is there for military aircraft. But still, this sort of feature you can see with a naked eye without any instrument. You can see this. If you are close to the plane, you can see some structure like this forming. This also gets formed in rockets, exhaust of rocket. You can see something like this. Now, other one interesting feature which is not visible without instrument is this. So, if you look around an aeroplane, how there are some flow patterns which are basically called shock waves, which we'll study in more detail. So I'm just trying to give you examples. Where do we see compressibility effect and how do they look and what are their applications? Okay, so around a high speed aeroplane, this will not happen for a normal Boeing Boeing aircraft like passenger vehicles, but for a high speed vehicle like a Air Force plane, you see some structures like this, and this is formed using a special photography method which is known as Schlieren. Okay, so these are shocks. So these are the type of things we'll study. We'll study how these shocks are formed and what are the equations to describe these shocks. That will look into this course. So basically, I'm trying to give you some idea what to expect and what we'll be looking forward in this course. Okay. So basically, what happens is, as someone has told, we'll talk about Mach number. So if Mach number is less than 1 or more than 1, we have different regimes. So Mach number also will define as the ratio of local flow velocity divided by velocity of sound at that region. So for, let us say, if the Mach number is less than 1, when we have subsonic flow, what will happen is that the streamlines get curved around that object. Okay, for example, let us see that this object is here, but if you look at this streamline, it is started curving before it approaches this. Okay, let me draw it. So here in this region, see that it starts moving out. Okay, why? Because some information has traveled upstream. Okay, the fluid particle here, it knows that some object or some obstruction is coming and I have to change my path. So it is turning around. Now what happens here is this fluid particle, whatever is coming from the left side, it has no idea that some object is sitting here till it reaches this shock. So this is called shock wave. That we'll study. Okay. So fluid particle coming from left, it is coming as if nothing is there, and then it hits the shock wave and then it takes an abrupt turn. Right? So the two key differences in these two images, one is that the change in path of fluid particle is smooth here. Okay, it is following a curve. It is taking a turn. Gradually, it is turning away from the object. Here, there is a sharp change in direction. It encounters a shock wave, and then it turns suddenly. Secondly, the information that any object is here or the disturbance, it is passed upstream. Upstream particle knows that something is coming, so I have to change my path. Here, that information is not passed. This fluid particle does not know that something is there until it reaches here. Okay, is this clear? These are the basic flow feature differences in subsonic and supersonic flow. Is this clear? Or any questions on this? Please stop me when you don't understand and ask questions or tell you don't know or you know. Otherwise, it will be very boring. What do you want? This is clear to everyone?
Yes, sir.
Yes, sir.
Fine. Now, when we talk about these types of flow, we'll be talking about compressible flow. What are the effects of compressibility? Then we'll talk about shock. And a very important parameter here is Mach number. That we'll define. Now, first let us try to understand what is compressibility, or when do we call the flow is compressible. Okay, so to define compressibility, I'll talk about bulk modulus or volume modulus of elasticity. So this can be defined as stress divided by strain. Now, let us say I have a flow like this. Let me get the pointer. Okay, so these are the stream tubes. Can anyone define what is a stream tube? You know what is a streamline?
Yes, sir.
So can you tell me what is a streamline?
No, sir, a streamline is a imaginary line which is drawn in a flow
Yes,
field in such a manner that tangent to the streamline gives the direction of the flow field.
direction of velocity.
Direction of
So at,
velocity. Yes, sir.
yes, so at all the points on the streamline, if you take a tangent, that will give you the direction of velocity. So the idea is that a fluid particle will not cross a streamline because the velocity is always tangent. Okay, now if I take a bunch of streamlines, I can make a tube like this. Okay, because the fluid velocity is always tangent to it, fluid particle will not cross the streamline, and this could be like a physical tube. Actually, there is no tube here, but I can imagine that I place a tube and fluid is flowing inside the tube. So that is what we call stream tube. Okay, so okay, for in general, let us say that we have a flow. Some fluid is flowing from here to here. Now here initially I have pressure as P and volume as V. Now what happens is that the pressure changes. Let us say I have P plus delta P. Okay, and because of that the volume also changes. Generally, if you increase the pressure, the fluid will get compressed. Now, to keep it simple or general, I have taken delta P and delta V. So we'll see how it changes. Okay, now what is the stress here? Stress is defined as force per unit area. So how you can define stress in a fluid? Can I write pressure as stress?
No, sir.
Why? How do you find pressure? So when you take, let us say, let me draw a simple example. So let us say I have a piston cylinder arrangement. Okay, I have a piston here. I have some gas filled inside, which is exerting some pressure. Okay, so if I want to calculate the force on this piston, cannot I say that force on that piston is equal to, let us say, delta P. Okay, delta P will be the difference between pressure inside and outside into A. Can I write like this or not?
Yes, sir.
Okay, so can I say that pressure is equal to force divided by area? If I take area from here to here, I can say that pressure is, or delta P is, force divided by area. You all agree?
Yes.
Okay, so that I can say that it is equal to stress. Now what about strain? Strain can I write like this? Delta V by V. This is how we define strain. That volume has changed by delta V. V is the original volume. So this is how we define stress by strain. Okay? Is it clear to everyone?
Yes, sir.
Okay, now can anyone tell why there is a minus sign here?
The difference is negative. I mean, it's decreasing, so the gradient is
Yes. So if
decreasing.
I
So to make it positive,
yes, so if pressure is delta P is positive, so if you increase the pressure, volume will decrease. So this will be negative. But this term E that I want to be positive. So because of that, I am putting a negative sign here. Okay. Now we also know that PV is equal to RT. This is for any ideal gas or perfect gas. assuming a molar 1 mole of composition. Now I can write P pressure as P plus delta P. Here I have P, here I have P plus delta P. So the same expression I write here. Here pressure for this region, the pressure is P plus delta P, volume is V plus delta V, right? So write P plus delta P and V plus delta P. This is equal to RT. Now if I expand this, if I multiply these two brackets, this is what I am going to get. PV into P delta V plus V delta P plus delta P delta P. Is it right? I'm just multiplying these two brackets. That's all. You people are following or not following?
Yes, sir. Follow.
So just keep talking. So I will also make sure
Yes, sir,
that I am connected and not lost the connection. If see again I am telling, if you are confused, any difficulty, immediately stop me. Fine. Now we know that PV is going to this much. So I will cancel some terms. PV will get cancelled from here. We are having these two terms, and this also I will cancel, because let us say that this is the second order term. Let us say that it approaches 0. It will be very small, so I neglect this term. So finally I have this is equal to 0. Okay. From this equation, I can write, if I take all this in RHS, I can write P is equal to V delta P divided by delta V, and again minus will come. Or I can write P is equal to minus of delta P divided by delta V by V. Fine. Now we also see that this is how we defined E. If you look at these two expressions, these are the same. Okay, so I can say that pressure can also be used in place of E, or compressibility can also be defined as volume modulus of pressure. So this is what is called volume modulus. Volume modulus of pressure is also defined as compressibility. Is it fine?
Yes.
Okay. Or I can write E in this form also, minus V dP by dV. So this is just the same equation in a different form. Moving on. Okay, I have not done animation properly. So for a flow like this, now let us talk about density also. Okay. So let us say I have a density rho here, and here rho is rho plus delta rho. So this delta could be positive or negative, but in general I am taking plus delta rho. Okay. Now how do I define my mass flow rate per unit area is rho into V. Now this rho V can be expanded like this, because m dot is same from here, for here and here, right? So m dot is rho V here, and rho plus delta rho and V plus delta rho, V plus delta V. Alright? So similarly I'm writing here. Now if I expand, same way we'll cancel some terms and we'll end up with this. Okay, now if I do some rearrangement, this will become like this, and similarly this is what we had in the last slide. Okay, now if I replace, sorry, so if you see, look at these equations, you can also say that compressibility can be defined as the density modulus of pressure. Okay, so instead of talking about in terms of volume, we can also talk in terms of density. Okay, so if I'm not getting any questions, I assume that you all are clear with whatever I am deriving here. Fine. Yes, any question?
No, sir.
Okay. Yes, is someone trying to speak? Please ask, or I'll go forward to the next topic. Okay. Now the question is that when I can say that the flow is compressible. Okay, so generally the general convention is that you take 5% change in fluid density, or delta rho by rho is less than 0.05 or 5%. So this is a convention. Okay, if you want, you can define it to be 4%, 10%. But generally, in all the textbooks, you will see that the general convention is 5% change in density. Then we say that the flow has become compressible, or compressibility effects have become appreciable. We need to take the effect of compressibility in all the equations that we derive or we calculate some values for the fluid. Now, I will also define Mach number, which we talked about previously. So Mach number is the ratio of velocity of the fluid, local velocity of the fluid, because velocity could vary from point to point, and what is the speed of sound at that particular location. Okay, E is for speed of sound. So based on Mach number, we'll define flow regimes that we'll see in subsequent slides. Now let us talk about sound waves. Okay, so sound waves are basically infinitely small pressure disturbance. Okay, so when we speak, we create very small pressure disturbance which are propagating in your room or whatever, and that is what you hear. So for example, in a human throat, we have something called vocal cords, which are shown here. So vocal cord of a person, they vibrate and they produce very small pressure waves which we hear as sound. For example, in your speaker, you have a speaker connected to your radio or computer. So in that speaker, you have a diaphragm which moves. Okay, as you can see here. So this moving diaphragm creates disturbance. It creates pressure pulse, a very small pressure pulse, which we hear as sound. Okay. Now we look at how to derive velocity of sound or speed of sound. So basically, imagine that we have a tube or pipe, whatever you think, and at one end we have stationary gas at pressure P. Okay. Now from here we create a pressure pulse. Okay, by any means. Let us say that I have a small piston which is suddenly started. So what will happen because of that? We draw it for you. So there's a tube, and let us say there's a piston here at the end. So it is a stationary fluid filled inside. Now I suddenly pushed this piston. So what will happen? It will create a small pressure jump. The pressure will be high here, and the fluid is moving at some velocity, let us say dV. So with dV, the fluid is moving in this direction. Okay, while at this side we have a stationary gas. Gas is lying there at pressure P. Now we also have a sound wave which is shown in red here, that is traveling towards right with a velocity a. So this is what we want to find, right? How much is the speed of sound in a particular medium? Are you clear with the example what we are talking here?
Yes.
Okay, so this is how you see if you are standing there from a lab reference frame, we see that the observer is stationary, and we see that one sound wave is moving from left to right. Okay, now for general analysis for deriving equations, we assume that the observer is sitting on the wave, or he is moving along with the wave. So what will happen if suppose my observer is sitting on the wave, we are on the reference frame of that sound wave, right? So what will be the velocity of let us say the stationary glass? Will it still be stationary? You heard the question. I am saying that if my observer or frame of reference is this wave, I am moving along with this wave. So what will be the velocity of this stationary gas? Will it still appear stationary, or I will see that it is coming towards me? What will happen? If I am sitting on this wave, I am traveling to right. Relatively, what I will be seeing.
It will move in opposite direction of velocity A.
Correct. So I will see that this gas is coming towards me. Okay, so this is how we'll see that this gas is coming towards me with the speed A. Okay, this is not acceleration, this is speed of sound A. I am moving with the wave, so now the stationary gas is towards me, and the velocity of gases is A minus dv. Earlier it was dv. Now since the observer is moving, so I will add A and I will minus dv. Is it fine?
Yes.
Okay. So now let us derive some equations. And this is the control volume. I will talk about, I will take that pressure pulse or wave inside a control volume, and then I will derive equations for this control volume. Okay. So now let us talk about conservation of momentum. So in general, in fluid mechanics, we'll talk about conservation of mass, momentum, and energy. Okay. So begin with momentum. The conservation of momentum says that it is basically based on Newton's second law. It says that whatever the applied or unbalanced force is there, that is your change in momentum. Right? So if this is my control volume, what is the unbalanced force on this? How much force is being applied? So can I say that unbalanced force is the difference in pressure? Here I have P plus dP, here I have P, right? So the difference is P minus P plus dP. Is this okay?
Yes, sir.
Okay. Now this is equal to change in momentum. What is momentum? M into V. So M dot is the rate of flow, and then mass flow rate of flow, and velocity one side is A minus dV. Velocity here is A. So delta V is this. Now M dot is rho VA, or A, instead of V we have A. So we say that using this I can say dP, okay, is equal to rho A dV. How that will come? This will get cancelled, A will get cancelled from here. So you have dP is equal to rho into small a into dV, this dV. Okay. Now let us talk about conservation of mass. Okay. So what is the mass that is entering from the left side? Rho into A. Okay. What is the mass that is leaving? Rho plus delta rho, change in the density, plus A minus dV. So this will give you d rho by rho is equal to dV by A. And if you use this and this, you combine these two equations, I can say that A square, see A is there in both of them, A square is equal to del P by del rho. Okay. And this is generally for a sound wave like this, we assume that this is isentropic. So the entropy is constant. Or I can say that this is called Laplace equation. And this is true for all fluids. So for the speed of sound, I can say that A is equal to del rho by del P by del rho for isentropic conditions. Fine. So this is how we can define speed of sound for any particular medium. Now let us also, as I mentioned, that this is isentropic. So for any isentropic flow, I can say that P by rho to the power gamma is equal to constant. And we also have A square is equal to this, that we have got in the last slide. Now using this, can I say A square is equal to gamma P by rho? Can I say this using this and this? Is this correct to say?
Yes, sir.
Fine. Now P is equal to rho RT for perfect gas. Okay, perfect or an ideal gas, I can say that P is equal to rho RT. If I use that in this equation, if you substitute, you will get A is equal to gamma RT, square root of gamma RT. This is another important equation which will be used to calculate velocity of sound or speed of sound. Okay, moving on. So if you want to look at speed of sound at different temperatures or what is the Mach number, you can go on to this website. So they have a very good app, online app. So you can enter whatever temperature you want, whatever speed you want, and it will calculate and give you what is the speed of sound and Mach number. So we'll also look at equations what are used to calculate, but same thing we can do on this online app. So you can try or check your calculations, or you can see what are the different ranges. We actually, this site you will find a lot of useful information, lot of interesting videos related to this course. So I will suggest you please check this site once. Moving on. So I also talked about heat generation, heat getting generated. So in the initial slides, we talked what is different in compressible flow, what is not there in fluid mechanics, what we don't talk about much in normal or general course of fluid mechanics. So one of the examples is this re-entry vehicle. Okay, you see that this is getting heated. There's a heat shield there, and it generates a lot of heat. While if you look at an passenger aircraft like this, it will also have a lot of drag, but it will not get heated like this. So the question is, why that airplane is not getting heated? While this is getting enormous amount of heat. In fact, if you heard about Kalpana Chawla, so her group died in this re-entry vehicle. When they are trying to enter the Earth atmosphere, it becomes so hot that everyone got burnt. But this type of thing is not heard of in a plane. So in fact, if the nose region, it is quite cool as compared to this. So what is the difference between these two? A space vehicle or a plane? What could be the possible reason? Anything related to velocity?
So the speed of the re-entry vehicle might be far more than what
Yes.
is for the plane.
Correct. So if you look at Schlieren images, so these are some images in the initial years when we are trying to develop space re-entry vehicles, mostly I think from NASA group. So what you can see, can you see any different or distinctive feature which we have already discussed? Anything very different in these images which you don't see in normal flow? So can you see something? Look at this wave. What is this? These are shock waves. Okay. Shock wave will be generated when your fluid velocity is higher than the sound velocity. So which means that these re-entry vehicles are at a much higher Mach number as compared to a normal aeroplane. Because of that, they are getting heated so much. Okay, I think we can talk about temperature. We'll stop here for today. I have to go for a department meeting. So any questions on what we have discussed so far?